All right, ladies and gentlemen. All right, so in the last video, you learned how to solve problems when you were missing percent abundance. These next two questions contain a different piece of missing information. So in these next two, you are going to be missing, let's see, we've got exact atomic masses, bromine 79, there's its exact atomic mass. It tells you the average atomic mass, and then in this question, it asks what is the atomic mass of the other isotope. So in this case, you're given the answer, but you're asked to backtrack and figure out something earlier. So let's write this out and make sure we know what we're doing. Whoops, sorry, I just dropped all my notebooks. All right, we've got bromine 79, and in this case, it gives us the exact atomic mass of bromine 79. So remember, just using the mass number as the mass is inexact. It's good for most things, but in this problem set, we're going to start moving on to using the exact mass. So it's going to be 78.918 AMUs. I didn't use units up here, and I should have. And we have our abundance. I'm going to write that down as 0.5069. And we want to add that to whatever the other isotope is, because bromine only has 2. So we don't know what that other isotope is, so I'm going to put X there. We do, however, and they also didn't give us the abundance. However, if there's only 2 isotopes, then these 2 abundances should add up to 100. So I'm going to write in 1 minus 0.5069. Okay, I could just do the math separately and then put that in. Absolutely, that would be fine. But this is just the way I usually solve these. Sometimes I write them out as like 50.69 over 100. That's fine too. This is just the shorter way of writing it, so I'm showing you this one today. And then it tells us the average atomic mass is 79.904 AMUs. Okay. So our job here is to solve for X. We could do this. So let's start out, this is just algebra at this point. Let's start out by trying to get this X all by itself on this problem. So we're going to do 79.904, that's this side, and we're going to subtract from that this chunk, minus 78.918 times 0.5069. Sorry, to pause it, a colleague walked in. We're subtracting this from this side and also from this side, minus 78.918 times 0.5069. So I'm going to do minus. This one has parentheses, so I get to avoid doing multiple steps. And you are welcome at this point in the year to use your own calculator. Okay, so that's going to leave me with X times 1 minus 0.5069 equals 39.9004658. Do you want me to write this out? Yeah, you probably do. Okay, so here we go. We've got X times 1 minus 0.5069 is equal to 39.90047. I'm rounding. Now I'm just going to divide both sides by 1 minus 0.5069. And that should give me X. Okay, so divided by parentheses. Okay, so X equals 80.9, we're going to round 92 AMUs. All right, that is the exact atomic mass of the isotope, which it's told us is bromine 81. Now, is it exactly 81? No, but that's okay. These atomic masses are not always exact. So there we go. That's good. Sometimes they won't even give you bromine 81. That won't even be in the problem. And in that case, you would get X and just round it to the nearest whole number. So in this case, if X is equal to 80 0.92. We would round that and say that's close enough to 81 for us to be sure that this is bromine 81. And that's actually what's going on here in question number 4. So pause this video, take a second, and try number 4 by yourself. I think you can get it. All right. So this one is set up very similarly to the other one. We're working with iridium this time. We know that one of the isotopes, there's only 2, one of them has an exact atomic weight of 190.96 AMUs, and the abundance is 37.3%. You can write this 37.3 over 100, but I prefer just to scoot the decimal so that I don't have to deal with that division problem. Okay, and then we would add that to the other isotope. We don't even know what it is this time, so we're just going to put in an X for that. And for its percent abundance, we know that if there's only 2, they must add up to 100. So it's just going to be 100% minus 37.3, or in decimal form, 1 minus 0.373. And we know that that will equal its atomic mass. Now, they didn't give us the atomic mass, but there is a hint. Use your periodic table to look up iridium. So here we go. Where's iridium? Here it is. And the atomic mass here is 192.22. 192.22 AMUs on average. All right. So we're solving this the exact same way we solved the last one. We're going to subtract this from both sides, then we're going to divide by this chunk. Okay. So I'm going to write this out minus 190.96 times 0.373 minus 190.96 times 0.373. If you prefer to do the math and then subtract whole numbers, that's totally fine. Makes no difference. So then we're going to divide both sides by this bit. Divided by 1 minus 0.373. 1 minus 0.373. I've been doing math for a long time, so I tend to just do it the way I know I can type it in my calculator easiest. And then when you get that, you're going to get x by itself. And x equals, when you do this math, go ahead and do that math. Pause the video, try it out. All right, I got 192.965 AMUs. What do you think? What is that? Well, 192 rounds to 193. We know that one of the isotopes was probably iridium 191 because this is pretty close to 191. This is probably iridium 193. So I'm going to make that, I'm betting that's my answer on this one. 193 iridium. I ran out of space, but there it is. That's my final answer. Okay. Now, I want to show you these problems on the inside. Got a couple more here. They're very similar to the ones on the outside with one difference. This problem number 5 requires you to do systems of equations. This is why we bothered teaching you them in math. It's for problems like this. So let me set this problem up for you, and then I will let you, once you've seen it set up, try to solve this on your own. We're going to need 2 equations for this one. We've got 2 isotopes, 35 and 37. We get the atomic weight. It's on the periodic table. But it doesn't give us either percent abundance. Okay, so let's set this up. I'm going to use A for the percent abundance of chlorine 35 and B for the percent abundance of chlorine 37. They didn't give me exact atomic weights. That's fine. We're just going to use 35 and 37, their atomic masses. And you're allowed to do that if they don't give you the exact ones. So 35 times A, the abundance of chlorine 35, plus 37 times B, the abundance of chlorine 37, and we know that that's going to equal the atomic weight of chlorine. So let's find the atomic weight of chlorine on here. 35.45. Okay. 35.45. Now, this would be impossible to solve if we didn't have values for A or B. However, we do have values for them. We can do a sneaky thing. We know that the abundance of A and B, if there's only those two isotopes, is going to equal 100. So we know A plus B is equal to 100. So what we can do is get one of these variables by itself, plug it in here, and then solve for that variable. Let me show you what I mean. I'm going to do minus A. I'm going to subtract A from both sides. So now I know that B is equal to 100 minus A. Okay. Now remember, we want to do this this is percents, and we want to use decimals, so it's actually going to be 1 minus A. All right. So then we're going to plug this in for B over here, and now our equation is 35A plus 37 times, originally we put B, but now we're going to do 1 minus A. Okay, and that's going to be equal to 35.45 AMUs. Okay, now we can solve for A, and that will give us the percent abundance of chlorine 35. And if we know A, then we can use this equation to find the percent abundance of chlorine 37. That's B. I'll let you finish up this problem. This is an example of about as hard as these problems get. 6, 7, 8, and 9 are similar to this one, and you will have to use systems of equations on a couple of them. Let's see. Do we want to finish solving this one? Yeah, I think I better should finish solving this one just so you can see an example of it. Okay, so this is going to be 35A plus 37 plus 37A when you distribute this. And that's going to be equal to 35.45. All right, well, let's combine like terms to make this a little bit easier. 35 plus 37 is 72A. Okay, we've combined those two, and I'm going to get rid of 37 on both sides. So now I've got 72A is equal to, yikes, this is ugly math. 72A is equal to, wait, that shouldn't have been negative. Did I make a mistake here? I did make a mistake. Did you catch it? When I distributed this, this should have been minus 37A. So this shouldn't be 72. 35A minus 37A is going to be negative 2A. And then when we subtract 37 from both sides, that's why this side is negative. So that's going to be, let's see, 35.45 minus 37, negative 1.55. Divide both sides by negative 2. And we're going to get A is equal to 0.775. Now, what is that in percents? Well, if we want to get a percent, we do times 100. That's going to give us 77.5% abundance. And remember, that's the abundance for chlorine 35. How about the abundance of 37? Well, that's pretty simple. To get that, we already have an equation for that. It's 100 minus A. So B equals 100 minus 77.5. And that's going to give us 22.5% abundance for chlorine 37. And this is 77.5 for chlorine 35. Okay, and I'm going to circle my final answers. So that's how you can find the percent abundances of two isotopes if you're only given the average atomic weight. Okay, we can do that using the systems of equations.